So now that we've seen an example of thermal expansion, or at least as we've seen thermal expansion, let's do an example of thermal expansion. So basically here what I have is a wall, and then attached to that are two pieces of metal which are attached directly to each other, where the one is lead and then the other one is aluminum. And initially these two start off with exactly the same amount of length, which we're going to call L0, so that's our initial amount of length. Each one of these two are different metal, meaning that they have two different linear coefficients of thermal expansion. These are their two different linear coefficients. Now what we're told is that under transfer of energy, i.e. heat, we're going to increase the temperature such that this entire system is going to increase by an amount of delta L, where we're told that delta L is equal to 1 millimeter, and we want to know then what is the change in temperature. So what is the overall change in temperature? So we don't know what the initial temperature is, we just know that it's at some initial temperature, but ultimately we don't care. All we really care about is what is our change in temperature. So how much temperature changed occurred as this thing was causing this thing to increase by 1 millimeter. Now, first thing to note is that since each one of these two guys has a different alpha, they're not both going to increase the same amount, even though the initial lengths are the same. But since they have two different alphas, then the increase of length is going to be different. Now, so what that means then is that the lead is going to increase a certain amount. So this is going to be our, say, delta L of the lead. And then here, the aluminum is also going to increase by an amount. So this is going to be delta L of aluminum. But ultimately what we know is that the amount that this one changes and the amount that this one changes have to sum together to equal the total amount of change. So from here we know then is that the change in total length must then be equal to the change in length of the lead plus then the change in length of the aluminum. Okay. Now in this case, again, we know the total change in length. We know that's 1 millimeter. So from here we can actually find the change in temperature. So under linear thermal expansion, what we know is that this is going to be equal to alpha of lead times the initial length of the lead times the change in temperature of the lead plus the alpha of aluminum times the initial length of the aluminum times the change in temperature of aluminum. Now, again, what we know is that they start off both with exactly the same amount of length to them, so we know those two things are the same. And what do we know about the changes of temperature? Do these guys have two separate changes of temperature? No. The change in temperature has to be exactly the same because we're changing the entire system at the same time. So what this means then is that the change in temperature of the lead must be equal to the change in temperature of the aluminum. So we know is that these two quantities are the same, so we can factor those out. So it's going to be equal to the coefficient for the aluminum plus the coefficient then for the lead times the initial length times the change in temperature. So from here we know the two alphas, we know the initial length. The only thing we don't know is that change in temperature. So if I solve this for the change in temperature, my change in temperature then is going to be equal to the change in length divided by alpha of the lead plus alpha of the aluminum times then the initial length. Now, let's do a quick dimensional analysis. So again, here this is a change in length divided by length. So change in length, it just has units of length. So this is length divided by length. So I have a 1 over alpha, but alpha has 1 over K, i.e. Kelvin, so that's a temperature. So this is 1 over temperature, which is the same thing as temperature. So I have change in temperature then is equal to temperature. So great. Dimensionally wise, this thing works out. So plug in my numbers, what I find in this case then is that my change in temperature is equal to 38.5 Kelvin, which is the same thing as 38.5 degrees Celsius. So remember that 1 degree change in Kelvin is exactly the same as 1 degree change in Celsius. So those two things are exactly the same. So good. So this is an example of linear thermal expansion. We're only going to do one. I think that's enough to kind of show what's going on. So